Plume behavior we have to discuss today. So the following are the plume types that we have to discuss. These are the important plume types because they help to understand under what condition there will be higher concentration of the pollutants or contaminants at the ground level. So these are the following types of plume that you have to remember: fanning, looping, fumigating, lofting, coning, trapping. And to remember this, we have the following codes. That is follow, fa for fanning, loop for the looping, few for fumigating, and low for the lofting. So fanning, looping, fumigating, lofting, these are the first four. The remaining two you can easily remember, that is just coning and trapping. So one by one in this sequence, you have to remember. First, we will discuss fanning, then looping, then fumigating, then lofting, and then coning and trapping. You can explain it easily. So let's see the fanning type of plume. So here, this is the fanning type of plume. So here you can see, just see the photo of the plume. So here you can see this is kind of plume which is under the condition of suppose fan. It is like that. Here a fan is installed, and this one is continuously pushing this plume in this particular direction. So that's why the name of this plume is fanning plume. So this occurs under the inversion condition or negative type of lapse rate condition in the atmosphere. So here you can see that when the DALR is just reducing here in this particular case, here the ELR, environmental lapse rate, is increasing with the increasing height in the atmosphere. So this is the temperature, this is the height. So this takes place in the extremely stable atmosphere where the ELR is more than the DALR value here you can see. So here more than not this is just inversion condition. So inversion condition is just associated with the stable atmosphere. So here you can see the dispersion of pollutants stops due to the absence of turbulence. So because the temperature is high in the above place, so the colder air in the downside, the warmer air in the upside. So here in this place, no mixing takes place. If no mixing takes place, so the pollutant will just in a straight path. So that is fanning type of plume. So generally formed during the late evening time or early morning time or in the winter time when the downside temperature is very, very low as compared to the upper side due to the very high winter, severe winter condition. So only on those situations, fanning type of plume is observed. What is important here? The inversion condition associated with the fanning plume is important here. And this particular diagram is very, very important here in all the plumes. So their condition and the diagrams. That's all you have to remember. You can find out multiple questions from the previous year papers asked from this particular section. Then we have looping. So loops are created here. This is, you can see, loops type of the circles you can find out here in the looping plume. Looping plume is just opposite of the fanning plume. In the fanning, the fan-like structure would be there. In the looping, loop type of structure is there. In the fanning, inversion condition is prevalent there, stable condition is prevalent there, and here unstable condition is prevalent here. The DALR, ELR value is like this. ELR value is more as compared to DALR here you can see. And this is completely unstable type of situation where well mixing takes place. And I have already told you unstabilities or strong instabilities are very, very beneficial for the pollutant dispersion. So here you can see pollution is not are keeping on one place. It is just going away easily by the dispersion of that. So occurs at unstable type of atmospheric condition that only occurs during the noon time, after noon time or during the daytime. So high probability of high concentrations sporadically at ground level close to the stack. It is not that much beneficial, but still it is beneficial because of the unstable environment. This is the looping plume. So this graph you have to remember, again very important. Then we have the fumigating plume. Fumigating plume is worst among all the plumes. So here you can see in the fumigating plume, an inversion layer is created just above the stack. So here temperature was decreasing. Again, it is increasing. So because it is increasing, it means here the warmer air is present and this is the colder air. So the colder air cannot go above of the warmer air because the colder air is more denser here. So here you can see this is DLR fixed. Is this ELR, the temperature is decreasing. Suddenly there is a inversion layer here. And now again, the temperature will increase. So pollutant cannot go up high in the atmosphere. All the pollutants will go to the ground side, to the downside. So that is a kind of fumigation taking place. So there is fumigating plume. This is a dangerous type of plume created when atmospheric conditions are stable above the plume and unstable below. So here there is inversion, means this is a stable condition, and this is lapse rate. So this is unstable condition. Lapse rate condition below and inversion condition above the stack height, certain height can be seen here. Then we have the lofting type of plume. Here, this is just opposite of the fumigating. There would be above stack height, there was inversion layer. Here, opposite will take place. The inversion layer would be just below the stack height. So all the pollutants will go up in the atmosphere. No pollutant is coming down. The formation takes place when atmospheric conditions are unstable above the plume. So here there is an unstable condition which we want, and this is stable condition or inversion condition. So there was inversion in the lower layer. After just is that height, again normal ELR is there, lapse rate is there. So inversion conditions below the stack and lapse rate condition above the stack is found here in the lofting plume. So this is the graph of the lofting plume that you have to remember. Then coning plume. So coning plume, because the kind of cone formation takes place here, that's why it is called as the coning plume. So occurs in the neutral atmospheric condition. So DLR, ELR both are equal here. This is DLR and this is your ELR. Or you can say ELR is not changing at all. ELR is just fixed in a one place. No change in temperature with increasing height. So this is associated with the overcast type of situation or cloudy type of situation. So pollutants travel fairly long distance before reaching ground level in the significant amount, which is also a good thing. So no problem with the coning plume as well. So occurs in the neutral condition or cloudy condition that you have to remember. Then we have the trapping plume. Trapping plume. So here you can see two inversion layers are formed here. One above the stack, another one is below the stack. So just there would be trapped pollutants here in between the two layers. So here temperature was increasing, inversion layer is there. So again temperature is decreasing, and again temperature is increasing because above that inversion layer. So such a type of graph is formed here, and this is your DALR dash line. So when inversion layer exists above the emission source as well as below the emission source, emitted plume will neither go up nor go down. Stable condition above as well below this stack, because this is inversion. In the inversion, I have told you there is a stable condition, and only in between the two layers, this is the unstable condition. Trapped in that particular unstable layer. So this is what trapping plume is. So I hope this is all the 6 type of plumes which are very clear to you right now. Such a type of questions you can see from this particular lapse rate question, the numerical questions. At a given urban location, the temperature at height 25 meter is 15 degrees Celsius. So this is surface at the 25-meter height, 15 degrees Celsius. ELR provided here is 1.25 degree Celsius per 100 meter. Or you can say this is equals to 12.5 degrees Celsius per kilometer. That is environmental lapse rate. If inversion condition occurs, it means this is not decreasing. The temperature is increasing here by 12.5 degrees Celsius per kilometer. The temperature is increasing here. This side is your temperature. This side is your height. What would be the temperature at 200 meter? So at 200 meter, definitely there would be more temperature than the 12.5 degrees Celsius, because 12.5 degrees Celsius already we have. 15 degrees Celsius we have in the 25 meter. This is suppose 25-meter height. And in this 25-meter height, we have the 15 degrees Celsius temperature. Now it is asking about the 200-meter above. Suppose this is the 200-meter height. So it is asking about the temperature in this height. So that's what we have to calculate. So definitely the temperature would be more than 15 degrees Celsius because there is inversion condition it is saying. It means the temperature is increasing with the increasing height. So two options definitely wrong here, 12.5, 12.75, because both are true only in that scenario when temperature will decrease with the increasing height. But here temperature is increasing with the increasing height. So that's why here the thing would be like this. 25-meter height, we have 15 degrees Celsius. So 25 meter to 200 meters. So 200 meter minus 25 meter, that is equals to 175 meter. And it is saying that in per 100 meter, the temperature is increased by 1.25 degrees Celsius. So for 175 meter, the temperature will increase by, so this would be 175 multiplied by 1.25. This is divided by 100. So this you have to solve. You will just get your answer. So 175 multiplied by 1.25 divided by 100. That would be somewhere around 1.75. So 15 degrees Celsius plus 1.75, 1.75 or 1.5, you can take approximation I am doing here. So in this approximation, you can see that the value you are getting is around 1.7, 1.5. So the value you will get is something wrong I am doing here. 175 to 80. Not 1.75 you are not getting. You will get somewhere around value 218, around 2.8 or 2.2. So 2 degrees Celsius of increase you can see here. So this is 15 degrees Celsius earlier plus 2.2 degrees Celsius again here, and this 15 plus 2.2 would be 17.2. So 17.25 is the right answer here, which is the closest option. So here two options, 17.5, 17.25 were here. You can just do the approximation by your own mind as well. At 25 meter, we have 15 degrees Celsius. If I go to 125 meter, so 1.25 would be increased. That would be 16.25, right? Again, 75 meter, I am going ahead. So now not full 100 meter. So in full 100 meter, 1.25 I was noticing increase. But this time I will show only, or I will see only 1 degree Celsius approximation increase, because this time it is not full 100 meter. So that's why the total temperature would be somewhere around 2.25 degrees Celsius. So that easy calculation you can do in your mind as well. Otherwise, this concept also this you can use. It is up to you. I am keeping it up to you. Whatever you like, you can use. Next question is similar to that. A temperature at a dry atmosphere at height 2 meter and 252 meter is 14.5, 12.5. So suppose this is the 2 meter height. At 2 meter height, we have 14.5 degrees Celsius. Then we have 252 meter height, and this is having 12.5 degrees Celsius. So the difference between them is 200 meter. And in this 200 meter, you can see that the temperature is decreased by 2 degrees Celsius. So the lapse rate here we can see here is equals to 2 degrees Celsius per 200 meter. So for 1 kilometer, this would be 2 degrees Celsius multiplied by 1000 divided by 200. So that would be equals to 100 per kilometer value. That would be 5 multiplied by 2. That is 10 degrees Celsius decrease in per kilometer value. And we know that 9.8 degrees Celsius is the value of DALR. So the question is saying that you have to tell the condition of the atmosphere is. The condition of a small atmosphere is whether unstable or stable. So we have or conditionally unstable. So we have the value of the ELR here. The ELR value we are getting here from the calculation is 10 degrees Celsius per kilometer. DALR value we already know that is 9.8 degrees Celsius per kilometer. So clearly we can see that the ELR value is more than DALR value. So here you can see that atmosphere is unstable, but in the unstable also we have two values. One is the conditionally unstable, another one is the fully unstable. So here 2 degrees Celsius for the per 200 meter. So for 10 degrees Celsius for the full 1 kilometer. So 1 degree Celsius, 10 degrees Celsius. So here clearly you can see ELR is more than DLR, and this is just signing of the unstable type of environment. Or what kind of unstable? Absolutely unstable, because ELR is more than the DLR. Conditionally unstable when ELR would be less than the DLR. So I hope this question is clear to you. Wait. There is a problem here in this question. We are just seeing the temperature difference here. 14.5 and 12.5, it is reduced to the height of that particular condition. Okay. So one mistake we were doing here, this is actually 250 meters. So 250 meter in this scenario, this is 252 minus 2 is 250 meter is here. So 250 meter, the calculation we have done here is for 200 meter actually. So this is not multiplied by 5, this is multiplied by 4. So here this is only 8 degrees Celsius per kilometer. So on that scenario, the ELR value we are getting is 8, not 10, which is less than the DLR. So that one mistake we were doing here. So that's why the answer were wrong. Here the right answer would be the stable type of environment, because the ELR value is less than the DLR, which is clearly we can see here. So I hope this is clear to you, and this is what type of numerical questions you can get in the examination of UGC NET that you can see here. So next question we will see in the next class. So that will be the next day. So meet you in the next class. Tomorrow we will complete this air pollution unit, as well as we will start the new unit that would be our maybe solid waste. So that we will start by tomorrow. So meet you all in the next class.